In this video, we cover Phasor notation. So Phasor notations are commonly used as a shorthand notation for sinusoidal signals, and they are widely used in electrical engineering and many branches of engineering. To show why a Phasor notation is normally used and how it can simplify calculations, I will start with a certain example of a trigonometric function that we want to simplify. So in this case, we have this waveform, this signal, which is a times sine omega t plus theta minus a times sine of omega t. And we want to simplify this into a more compact trigonometric representation. So we start with, so there are some details related to the calculation, but that is not really important here. It's just a motivation of why a phasor notation is a convenient way to represent sinusoidal signals. So let's walk through the calculation once. So if we have a sine omega t plus theta, we can expand it into a form like this: a sine omega t cos theta plus a cos omega t into sine theta. And then taking the common terms, this can be represented by this equation here. And then it's possible we want to represent it as a single sinusoidal wave. Then we divide, take the square root of this magnitude, these two components, which is shown here. So a square sine square theta plus a square times 1 minus cos theta whole square, and on simplification this gives 2a square into 1 minus cos theta. And then if we divide this by this equation by square root of this term 2a square 1 minus cos theta, both the on the top, and then we divide it by this term, then it is given by this equation here. And then with further simplification we can eventually arrive at the equation 1 here. And point that I wanted to illustrate here is that in this equation, if we see, we keep using terms like this again and again: cos omega t, sin omega t, and in every simplification that we do, we are using these terms, and then we eventually arrive at the final equation. So the Phasor notation helps to simplify this calculation by simplifying the notation, that we don't have to write this cos omega t, sin omega t every time. We already know that we are dealing with a sinusoidal signal of frequency omega. So all we need to know is the amplitude of, say, a particular sine wave and what is its phase related to that. So in this case, cos omega t or sin omega t, and they may have a phase of 90 degrees. So in other words, for a sinusoidal signal, we only need to know the amplitude and the phase for a fixed sinusoidal signal, and we do not have to keep writing sin omega t and cos omega t every time in every step of the calculation. That's what the Phasor notation comes in, and that's the motivation of why the Phasor notation has been introduced. And it also helps with some visualization in terms of the phase and amplitude of the sinusoidal signals. So before, there should be some background of complex numbers to understand next how the Phasor representation is used. So this is a well-known Euler's formula in complex numbers, where e to the power j theta is cos theta plus j times sin theta, where j is the imaginary square root of minus 1, is an imaginary number, and is basically referred to as the square root of minus 1. And if with this notation, if we have a sinusoidal signal a times cos of omega t plus theta, this can be actually written as a times a real part of a complex number, which is defined as cos omega t plus theta plus j times sin omega t plus theta. So because this is a complex number, so the imaginary part is sin omega t plus theta and real part is cos omega t plus theta. We take the real part of this and we'll get a cos omega t plus theta. And using the Euler's formula, this expression, this whole expression, can be written as e times e to the power j of omega t plus theta, and this can be simplified as a real part of a times a into e to the power j theta into e to the power j omega t. So why we took real part? That's the common notation, but we could have as well defined the Phasors in terms of the imaginary part, and we could arrive at the similar results and it won't change a thing. But it's just a notation that is commonly used. And in this case, e to the power j omega t refers to the sinusoidal signal. And in our earlier calculation, when we were using cos omega t, sin omega t again and again, we want to avoid that. So instead of having this information, which is in a way redundant, once you know what's the frequency is, we only need to know what's the amplitude and the phase of the signals is. And that's where the Phasor representation comes. So in a way, if you want to represent a sinusoidal signal, a cos omega t plus theta, we only need to represent it as a amplitude followed by what's the phase associated with this. And in complex numbers, this means a into e to the power j theta. And we can now repeat the same calculation. So we started with this expression, and now we'll see we want to simplify this using Phasor notation. And it will show that, okay, we do not have to write the sin omega t, cos omega t, these functions again and again. So we start with the a sin omega t plus theta, and instead of sine, we write it in the cos form, a cos omega t plus theta minus pi by 2. And in this case, if you look at the phase, we can write this term in the Phasor form as shown here, a into e to the power j theta minus pi by 2. And similarly, for sine of omega t, we can write this expression in terms of cos as omega t minus pi by 2, and then write this term here as the Phasor representation of a times sine of omega t. So now we have for each of these two component signals, we have represented it by Phasor. And if you want to simplify it, we will just put the phasors in place of the actual sine signals here. So in this case, we replace the first term, a sin omega t plus theta, by a e to the power j theta minus pi by 2, and a sin omega t by a to the power minus j pi by 2. And we can further simplify this as shown here, and there are some it can be if you're familiar with complex numbers, then you can show that e to the power minus j pi by 2 is equal to minus j. And then substituting this and simplifying this expression, we eventually arrive at here at this place, which is a complex number representation after the simplification here. And we can write it into a what is called polar form in complex numbers, where the first term represents the amplitude and the second term represents the angle of the complex numbers. And in this case, so we have represented the expression that we had begun with simplifying into a Phasor notation eventually here by this term. So this is the Phasor representation of the expression that we started with. And note that in this calculation here, from here to here, we have not used any omega t dependence, because that is already implied in our earlier assumption. So that in a way has simplified the calculation, not perhaps not simplified, but in terms of notation, it has simplified the calculation. And then eventually what we want is the signal in the time domain. So once we have the Phasor, we know that this was the Phasor of the expression, this expression, and we know that we can get the time domain signal again back by using the definition of the phasors, which was shown here, that the original signal is nothing but the Phasor into e to the power j omega t and the real part of that signal. And we take the Phasor here, this Phasor number that we got here, and we put this into the expression for the real part of the Phasor representation into e to the power j omega t. And with a little bit of calculation, this numbers comes out to be a times root over the magnitude here, cos omega t plus alpha. And if we compare this equation with the earlier equation, where we had used brute force method with all the time dependencies also in the equations, we arrive as expected at the same result. And that's the utility of the Phasor. It's just a notation. There is nothing fundamental about this, and it helps to simplify the calculations and make the math look a bit clean. And this is what will be used later for calculation of impedances, and there are several other applications for Phasors. So in summary, if we have a signal like cos omega t plus theta, we can represent it by a phasor like this. And if we have a signal like a sin omega t plus theta, we can represent it using a phasor like this.